An insulated rigid tank contains 5 kilograms of argon gas at 520 kilopascals and 70 degrees Celsius. A valve is now opened and argon is allowed to escape until the pressure inside drops to 250 kilopascals. Assuming the argon remaining inside the tank has undergone a reversible adiabatic process, determine the final mass in the tank. As usual, try pausing here to solve this yourself before watching the solution. This is the third example for the reference entropy and specific heats main lecture. The link to that 12-minute lecture and all the other examples and lectures of the thermo course are found in the description below. The main concept that this problem tests is the understanding of isentropic processes. If we're being told that the tank is insulated, it means that the heat is not allowed in or out of this container. This means that the process is adiabatic, which is also given in the problem statement. And additionally, we're being told that the process was reversible. So if ds for a reversible process is equal to delta Q over T, and delta Q is 0, ds is 0, meaning that S1 is equal to S2. With that being the case, and it's always the case for a reversible adiabatic process, we can use the isentropic relationships that we derived in the main lecture video. Since what we want to find is the mass at state 2, and argon is an ideal gas, since the volumes and R didn't change, we have that M1T1 over P1 is equal to M2T2 over P2, and therefore M2 is equal to M1T1P2 over P1T2. We have all the values except for T2. This means that the relation that we derived in the main lecture video that we need here is the one that relates temperatures and pressures because we do have the pressures. From this expression, we solve for T2 and notice that we need the K ratio Cp over Cv. Since we don't know what the final temperature is gonna be, we can assume 300 Kelvin for now to get K, and substitute the values with T1 in Kelvin to find T2. Since with this value for T2 and T1, we would get an average of 300 Kelvin anyways, our K value is on point. If this wasn't the case, we would iterate by taking the new K value for the average temperature and calculate 2 again, and repeat this process until the temperature converges. We now go back to our mass equation, substitute all values, once again in Kelvin, and find the value for M2, the mass at the end of the process. If you want to check out other examples for the reference entropy and specific heat topic, make sure to check out the links I left down in the description below, where you'll also find the links to the other lectures of the Thermodynamics course. You'll also find the playlists to other engineering courses. Thanks for watching.